Hello, everyone. Welcome to pre-lecture 28. This is essentially just an overview of most of the material that will be on exam 4 as hopefully a way to be helpful for your studying in preparation for exam 4. So just to begin with, going back to chapter 16, discussing spontaneity. So a reminder that a spontaneous process is one that occurs naturally under certain conditions, whereas something that is non-spontaneous must be essentially driven, so have some sort of energy input from outside of the system in order to occur. Okay. So an example of that, of course, a couple examples of that are listed there. And also just a reminder that spontaneity has nothing to do with the speed of a reaction. That takes us back to kinetics. So the spontaneity of something has to do with the energetics of the reactants and the products. And so if we were considering an example of diamond and graphite, both of which are allotropes of carbon, diamond has a higher energy as a reactant. And so we would say that the graphite, to go from diamond to graphite is a spontaneous process, but it has a very large activation energy barrier. So of course that process is very, very slow. But because it is very slow, does not tell us anything about the actual energy states, right? And so ultimately this leads to a discussion of the dispersion of both energy and matter. And so if we start with the dispersion of matter, things that are more concentrated will move towards a more uniform dispersal of that matter under spontaneous conditions. And so the example here is, say you have one flask with gas and then one flask under vacuum. If you were to open a stopcock between them, then of course you would end up pretty quickly with a equal distribution of matter, because that is a spontaneous process. And if you wanted to reverse that, get that gas back into only one part, you would have to put in some sort of external energy into that system in order to drive that non-spontaneous process, right? Same could be said for heat. So if X block is hot, Y block is cold, then if we put them together, you will get again, dispersal of energy that is driven spontaneously. So that leads to a discussion of microstates and macrostates. And so just a reminder that we can essentially define what a microstate is by as being one possible arrangement of energy or matter within a system, whereas a macrostate is measured properties of that system. So something like temperature, pressure, beyond. This is important because entropy itself is what we use to quantify the amount of energy, or the dispersion of energy rather, within a system. We can quantify entropy as an absolute value using the Boltzmann equation here, where we have our entropy being equal to Boltzmann's constant times the natural log of W, which is of course our number of microstates. Okay. That leads us to a discussion of the third law of thermodynamics, where, again, this kind of sets our absolute scale for entropy, where we know that if we have a perfect crystal at 0 degrees Kelvin, our entropy will be 0, meaning there is no molecular motion, be it translation, rotation, vibration, and so our entropy would be 0 in that case. Of course, this is just theoretical. There are no perfect crystals that are at 0 degrees Kelvin out there, but it does help set our absolute scale for us with entropy. Okay. As far as predicting entropy, just by looking at a system, the entropy of solids will be less than liquids, which will be less than gases. So gases have the most entropy if you have a single element or compound in 3 different phases. If you have molecules that are in the same phase, and then you would want to look to their molar mass. So molecules in the same phase, ones that have larger molar masses will have greater entropies. And then if you form more moles of products as compared to reactants, then that would also represent an increase in energy. Okay. Finally, of course, phase transitions, kind of going with the first part there, that as we transition from solid liquid to gas, we would get an increase in our entropy as well. Okay. And so because we have this absolute value of entropy, we are able to basically have standard entropies. And so this is under standard conditions, where again, we're at 1 bar and 298 Kelvin. These are values that are listed in tables, and we can calculate the change in entropy for our system by taking the sum of those products minus the sum of the reactants. Our V term here is the stoichiometric coefficient that would be in front of them in a chemical reaction. And so can see our in-class worksheet for examples of how those are calculated. This leads us to a discussion of the second law of thermodynamics that allows us another way to predict whether something will be spontaneous. And the second law states that all spontaneous changes cause an increase in entropy of the universe. And so even if we have a non-spontaneous process going on in our system, we need or if we have a non-spontaneous process there, or a negative change in entropy in our system, maybe we go from having 3 moles of a reactant to 2 moles of product, then we would have to have a more positive change in the entropy of our surroundings, so that the entropy of the universe would increase. Okay, there's an example there with liquid water. Relating entropy to other thermodynamic properties, such as enthalpy, so that's delta H, can be important. And this is the equation here at the bottom of the slide that we would use to do that, where the entropy of our surroundings can be calculated by determining the negative enthalpy of the surroundings, which is temperature dependent. And so if you measure the enthalpy of something at a certain temperature, you can also then calculate the change in entropy for that process. And once we have discussed entropy and enthalpy, we can then, of course, bring in Gibbs free energy, which is kind of the be-all, end-all, the most precise way in order to measure the spontaneity of something. And it can be quantified using this equation here, where we have our Gibbs free energy being equal to our enthalpy minus the entropy at a certain temperature. And this Gibbs free energy represents the maximum amount of usable energy or work that can be produced. So things that are not work are typically just heat, basically enthalpy, or distribution of energy within microstates that can't be used for work. Just a reminder that negative delta G values are what we would call spontaneous or favorable, whereas positive delta G values, what we would call endergonic processes, are non-spontaneous. Okay. We can see that represented in this graph here, where again, for our exergonic processes, we have some sort of reaction that releases exergonic, so energy that is usable for work. And so our products would be then at a lower Gibbs free energy. And then the opposite would be true for an endergonic process. Of course, if we relate this back to our initial equation here, we know that certain processes will always be spontaneous. So if they have a negative enthalpy and a positive entropy, no matter what the temperature is, they'll always be spontaneous. And then the opposite is true, of course, then if we have a positive enthalpy, which is delta H, and a negative entropy, those will never be spontaneous. And then, of course, we have 2 situations where the entropy is dependent on our temperature, and ultimately that means the spontaneity is dependent. And so again, you just want to think about this second term here, and do we want to maximize or minimize that term in order to get a spontaneous process? So for example, if we have a positive delta S, then we would want a high temperature in order to get a more negative delta G, meaning that would be how we get a better spontaneous process. And so that would be this example, where at higher temperatures, we have an increase in entropy despite our process being endothermic. Okay. And this is just a different way to represent that. You'll see, of course, at certain temperatures, we would cross over from being non-spontaneous to spontaneous or spontaneous to non-spontaneous for certain processes. Right? Okay, and that brings us to, I guess, other ways to calculate Gibbs free energy. And so you can relate Gibbs free energy to equilibrium constants or systems at non-equilibriums using these bottom two equations here. You can also determine the change in Gibbs free energy by using values that are in your table. On the exam, those would, of course, be provided for you should you need them. Okay. All right, that finishes up chapter 16. So if we move on to chapter 17 then, talking about redox reactions, a reminder that reduction means a gain of electron, oxidation means loss of electrons. And within our oxidizing or within our redox reaction, an oxidizing reagent is a compound that gains electrons, so it is reduced, whereas a reducing reagent loses its electrons so that it is oxidized. Okay. Um, this is the process for assigning oxidation states. I won't go through it here because it would take us a while, and you guys have plenty of examples from class. The same is true for how we would balance our redox reactions in a systematic manner for either acidic or basic solution. And there are lots of practice problems at the end of chapter 17 in your textbook if you're looking for more practice to do there. Of course, you could always redo problems from Sapling as well. Okay. So if we think about these redox reactions with regards to how we would then measure their potential, we have these redox reaction if we just, for example, submerged copper wire in a solution containing silver, we could see a redox reaction occur. And it will occur spontaneously, but most of the time we want to separate out our redox reactions into two half cells where we would have an anode and a cathode. And so instead of our reaction taking place directly, we have an electrons flow through our circuits where we can measure a certain potential. Okay, and this is what we would call a galvanic or voltaic cell. You can use those terms interchangeably. Finally, or not finally, but within these voltaic cells, our cathode, so in this case, copper is where our oxidation, or sorry, our cathode is silver, is where reduction takes place. So our silver ions turn into silver metal as they are reduced. And then at our copper anode, we have copper metal dissolving as it is oxidized. And then we would also have a salt bridge that is used to help balance our charge. So we always have positive ions of our electrolyte flow towards our cathode and negative electrolytes flow towards our anode because that is driven by the flow of negative electrons. And so our salt bridge is there to balance our charge. Okay. We can, of course, use a specific electrode, the standard hydrogen electrode, in order to create a scale for chemical potential. So the standard hydrogen electrode is showed here, and it has a chemical potential of 0 volts. We can calculate the potential of any electrochemical cell by taking the reduction potentials from our cathode and subtracting the reduction potential of our anode. Okay. And so this is an example shown here where we have our standard hydrogen electrode and we're measuring the potential of copper. Okay. These values are also tabulated. They exist within tables. The more positive the potential is, the more oxidizing it is, whereas the more negative it is, the more reducing. I should also say that more positive potentials are more spontaneous, whereas more negative potentials are more non-spontaneous. Okay, so you can calculate the potential of a cell or the spontaneity using the equation discussed above, where if you identify the two metals that are involved or the two species, they don't have to be metals involved in an electrochemical cell, you would be able to determine the cell potential, standard cell potential that is. Also a reminder to not multiply any of the reduction potential values even if the reaction is multiplied to make coefficients balance. So in this case, we have silver and barium. If we multiplied our silver reaction by 2, so that we had 2 electrons transferred for both our anode and cathode reactions, we would not multiply our standard reduction potential value. Okay. Um, we can also relate this electrochemical potential to Gibbs free energy and our equilibrium constant K using this equation. You'll also need to note Faraday's constant, which will be provided for you on the exam, this 96,485 coulombs per mole electron. And then the chemical potential of the cell is this E standard cell. So we can relate basically, again, all of our equilibrium constants, Gibbs free energy, and cell potentials using these equations here. Reminder that when K is greater than 1, it will be spontaneously favorable towards the products. Anytime delta G is negative, that will be spontaneous, and then a positive electrochemical cell potential will also be spontaneous. Okay. Uh, and then coming up on the end here, we have the Nernst equation, which is what we would use when we're under non-standard conditions or not at equilibrium. So in that case, we use Q. And a reminder that Q is calculated by taking the concentration of our oxidized species divided by our reduced species. That is just our products over our reactants. And so it should be relatively easy to determine which is which, assuming you're able to write the chemical equation that's going on based on finding the relative reduction potentials in a table. Okay. That's it for now. We are going to cover a little bit of new material in class for lecture 17, or lecture 28 in class. And so I will see you then. If you have any questions, please feel free to let me know. Otherwise, happy studying.